Colleagues and guests, it is my great pleasure to open the third day. We have a very exciting day planned, and before we start this plenary session, I want to highlight that we have 13 technical sessions today and 2 poster sessions during the morning and afternoon breaks. In addition, there will be a lunchtime side event in room M3, and it will be on the IAEA's activities that are related to SMRs. This event will include presentations from various IAEA departments and perspectives from 3 embarking countries. And last, tonight we have a very exciting event, SMRs and microreactors towards a sustainable and equitable future. This is a young generation event, but all are welcome to participate. And it looks like instead of M3, the lunch side event is M1. It's this location right here. Thank you. The event this evening will include a multi-generational, multidisciplinary panel that will delve into the opportunities and challenges posed by SMRs and microreactors. And now to our plenary session. It's on innovative SMRs. As we gather here, we are reminded of the critical role that innovation in nuclear technology plays in addressing the global energy challenges of our time. With the increasing demand for clean, reliable, and sustainable energy, innovative SMRs offer promising solutions. Their flexibility, enhanced safety features, and potential for cost-effective deployment make them a key component to the future energy landscape. The IAEA has been at the forefront of promoting and supporting the development and safe, secure deployment of advanced nuclear technologies. Their commitment to advancing nuclear technologies is crucial in helping countries achieve their energy goals while ensuring safety, security, and sustainability. Today, we are very privileged to have with us a distinguished panel of experts who are at the forefront of innovative SMR research and development. Each of our speakers brings a wealth of knowledge and experience, and I'm confident that their presentations will inspire fruitful discussions and collaborations. Thank you so very much for joining us today, and I look forward to a productive and enlightening session. I will now turn it over to Anna Gomez and Vladimir Kriventsev to begin the panel discussion.
Thank you very much to our conference president for opening our plenary session on innovative SMRs. Good morning, dear colleagues. My name is Anna Gomez, and I work in the IAEA Department of Nuclear Safety and Security, where I am the head of the Safety Assessment Section. And I will be co-moderating this plenary together with my colleague, Vladimir Kriventsev, who works in the Department of Nuclear Energy and is the team leader for fast reactor technology development. Thank you very much for joining us today. We have a very exciting session of just over an hour ahead of us to discuss the latest advancements and future directions in innovative SMR designs. During this section, we will explore the breadth and diversity of innovative SMR concepts and the development globally, and we'll discuss the key challenges and opportunities for innovative SMR deployment. We will also highlight efforts made by regulators to enable the safe and secure deployment of innovative SMRs, and we'll emphasize the importance of international collaboration. I encourage you all to participate in the discussions, ask questions, and share your perspectives. And if you have suggestions for our work on innovative SMRs at the IAEA, we'll be delighted to hear them and take them forward. Now, I pass the floor to my colleague, Vladimir.
Thank you very much, Anna. Thank you for a nice introduction. And it's now my pleasure to introduce our panelists here. Could we see the first slide, please? And first is Dr. Stéphane Sarrat, who joined the French Commissariat of the Energy Atomic, okay, I cannot say it in French, which is we know as a CA in France in 1995. Since 2020, he is the CA Director of Energy Programs Directorate with responsibility for low-carbon energy R&D programs, including nuclear and renewable energy. Since 2023, Dr. Sarat is the vice-chair of the Generation 4 International Forum, and he will be assigned the chair of the GIF in 2025, correct? So for this, Stefan will provide an overview of the work of the GIF in general. Our next panelist is Dr. Sara Perez-Martin. She is a senior researcher at the Karlsruhe Institute of Technology in Germany, and Sara works in the field of safety assessment of sodium-cooled fast reactors. Dr. Perez will discuss the innovative approaches and safety features of the sodium-cooled fast reactor correspondingly. Another competitor for the sodium fast reactors is the lead-cooled fast reactors, and here today, Dr. Mariano Tarantina, who is the head of the division of the nuclear energy systems at the Italian National Agency for New Technologies, Energy, and Sustainable Economic Development, ENEA, we know these organizations. Dr. Tarantina has more than 20 years of experience in heavy liquid metal technology for nuclear applications, and he will provide an overview of the developments and potential of the lead-cooled nuclear systems. And then Mr. Frederick Reisma, it's here, with a little bit wrong setting, who has a more 25 years experience in high-temperature reactor designs and safety analysis. 13 years he spent on working in the Pebble Bed Modular Reactor project in South Africa, and since June this year, Frederick is the head of nuclear power technology development sections in the area, which I belong to, my boss. So, and our section covers all innovative reactor technology. Frederick will discuss technological aspects and advantages of the high-temperature gas-cooled reactors, all technology, and his presentations with very nice and interesting title, More Than Just Hot Air. It should be helium, I guess. Yeah? Then we have Professor Jan Lien Klosterman, who works in Technical University of Delft in Netherlands, and he is a full professor of nuclear reactor physics, head of research section of the reactor physics and nuclear materials, and a chair of the Department of Radiation Science and Technology. Professor Klosterman was involved in the molten salt reactor research more than 15 years, and he will, of course, discuss this molten salt reactor technology and this is benefits and challenges probably, especially in adaptation to SMRs. Last but not least, we have Ms. Sarah Jan Eton, and she is representing the big part of safety, it means from the regulator side. And Sarah is the director of the General of the Directorate of Advanced Reactor Technology at the Canadian Nuclear Safety Commission, where she works since 2009, I believe. And her responsibility is for licensing of new nuclear reactors, pre-licensing activities, including the vendor design review, and leading CNSC SMR readiness project. Sarah will address critical aspects of the safety and regulations for the advanced reactors. Welcome, and please listen to our panelists. Anna?
Thank you very much. So now we start with our first speaker, Stefan Sarat, please. The floor is yours.
Thank you for the...
Could we see the next slide, please? My green button doesn't work. Okay.
Seems to work. Thank you very much. Good morning, ladies and gentlemen, distinguished colleagues. It's a pleasure for me this morning to open this presentation. Of course, I'm from CEA, but this morning I will speak on the behalf of the Generation 4 International Forum, and I'm very honored to be the next chair with the incoming years from 25 to 27. So, what is GIF? GIF is more than 20 years in terms of expertise, and it was formed in 2001, and it's a multilateral international collaborative research and development, so focusing on R&D on the Gen 4 nuclear energy system. So we have 8 major technological goals defined for the Gen 4 system in the broad areas of course, sustainability, economics, safety and reliability, and proliferation resistance and physical protection. So GIF identified and focused R&D effort on historically 6 reactor technologies that could meet these goals. Of course, we have gas-cooled fast reactor, GFR, lead-cooled fast reactor, LFR, molten salt reactor, MSR, supercritical water-cooled reactor, SCWR, sodium-cooled fast reactor, SFR, and finally, very high-temperature reactor, VHTR. So GIF current membership includes 13 countries and Euratom, representing 27 European Union members. And of course, we are dealing with the support of OECD NEA for technical secretariat. So in terms of major goals, of course, we have sustainability, what it means in terms of long-term fuel supply, in terms of minimization of waste and long-term stewardship burden. We focus also on safety and reliability with excellence in safety and reliability, of course, very low likelihood and degree of core damage, eliminate need for off-site emergency response. We also work on economics with life cycle cost advantage over the other energy sources, with financial risk comparable to other energy projects. And then, finally, we also work on proliferation resistance and physical protection in terms of unattractive material diversion pathway and, of course, enhanced physical protection against terrorism. So the key mission for the past 3 years was accelerating the readiness of Gen 4 systems to meet the net zero goals, the 2050 net zero goals. So we strengthen a Gen 4 system feature for combating climate change with flexible operation and non-electric applications, which is an important point we developed. We support transition from R&D to demonstration and deployment in terms of TRL, but also in terms of regulatory readiness and improved economics. We strengthen GIF relevance to industry with industry engagement and close connection with industrial partners in this field. And we also have a senior industry advisory panel. And then we support the Gen 4 talent pipeline. It's very important for us to increase the attractivity of our field to young generation, to young talents, and we support development, demonstration, and deployment of what we can do on this field. In terms of SMR and AMR, I think we are all convinced that there is a great interest on modular reactor worldwide. SMR, AMR, SMR for us is 3rd generation, AMR is for us 4th generation, and they have a great potential from nuclear to X. We'll come back on this definition. And we are pretty convinced that they will be included as a part of the nuclear energy contribution to meet the net zero by 2050, and of course beyond. I'm pretty sure that you know this map, which is a dashboard of NEA showing recently all the projects, roughly 100 different projects in the world dealing with SMR and AMR. And then we are working on this field. We provide a foundation for the advancement of SMR and AMR because we share innovation, we share research in safety and efficiency. We collaborate in an international way, and we have a good vision of how to align long-term sustainability goals. And SMR and Generation 4 reactors share many technological and policy objectives, and GIF is nowadays currently an important platform for the continued development of SMR and AMR beyond electricity. Last week in London, we had the meeting of GIF, and it was my pleasure as a vice chair to present this slide, which is very important, which is a nuclear domino effect of 2024. Perhaps you know that, and it's connected with the GAFAM, Google, Amazon, Facebook, Apple, and Microsoft. And this is the nuclear domino effect, with Amazon starting with buying nuclear power data center from Talent Energy, and Microsoft signing with a Constellation to provide energy through the former reactor from TMI. Then more recently, Google's with a great deal with Kairos Power, and Kairos Power, the first reactors from Kairos Power is the first for 50 years. That is a non-LWR reactor that obtained the clearance for the construction in the US. 50 years. So it's a very important milestone. And more recently, Amazon, that invests more than 500 million euro to X-Energy to develop modular reactors. So we have facing a very important momentum. So collaboration are key for the successful development in this area. And of course, we have a great cooperation with IAEA, and the IAEA participation is in GIF. Methodology and working groups is very important for us. GIF IAEA interface meetings to coordinate collaborative efforts. We have a joint workshop on safety and advanced reactors, and we participate to the NC, Nuclear Harmonization and Standardization Innovative. It's very important for us. SIAP is also from GIF is very involved in that field, and for us, NC and Harmonize by Euratom are very important for us. So we also work on OECD and EA with a Committee on Nuclear Regulatory Activities, on safety nuclear installation, and on technical and economical studies on nuclear energy. And more recently, we joined European platforms as SNETP, Sustainable Nuclear Energy Technical Platform, and the recent Industrial Alliance on SMRs that was recently created. Thank you very much for your attention.
Thank you very much, Stefan. Really good overview of GIF and what we are dealing with here today. So our next panelist is Sara Perez Martin. Sara, please, the floor is yours.
Okay. Thank you very much. Good morning, ladies and gentlemen, and thank you for sure to the organizers of the conference for inviting me to participate in this panel. I will present you some key features and comparative advantages of sodium fast reactors for small modular reactors. So there is quite different topics where sodium performs good in terms of fuel, for instance, because it's under fast spectrum, which is the operation of the sodium fast reactor. So it means that the production of minor actinides, long-term storage is lower, so it's not needed. It could allow also the fuel cycle to be closed to recycle and transmute. And also for the core layout, it's foreseen to have safety performance. So we know problems or problem issues about reactivity insertion, so we can tackle these problems by doing a special cake shape for the core. So these are key features where we enhance, for instance, the neutron leakage, etc. I don't go in detail, but just to let you know the key features about this. Sodium itself, it has good qualities for boiling, for instance. It's high enough. There is a quite large margin for boiling, and the operation regime is also high. So this allows also flexibility in the design and operation. Heat transfer as well allows to have compact cores. So this is for the economics also good. And the reactor layout present a variety between loop design or pool, depending on the option. And then, for instance, for the pool option, the pumps are immersed. So it means that no LOCA is possible. It has a large inertia, so it provides additional inherent safety features. For the safety itself, as I mentioned, there are different ways on how to perform these safety measures. Safety measures can be applied to the fuel level by doing different design of the pins, heterogeneous or shorter in the core zone. There are different options. Passive systems are already included because of the natural circulation performance of sodium. The primary loop is under low pressure, so it means we don't have really to tackle that problem in a high pressure. And then the water-sodium interaction, which is also a chemical reaction we try to avoid, can be addressed by inserting a typical intermediate sodium loop in between the primary and the power conversion system. Another key feature to mention is that it has a large operational experience commercially, with more than 500 reactor years of experience. It includes also current projects in China, Russia, India, worldwide. So I would like to mention as well this last point, load following. So because of the high temperatures, we are talking about sodium temperatures between 350 and 500. This allows to have an intermediate thermal storage where with an affordable size we can store energy and then be in a load following mode, supporting the grid stability and the load operation. I'm presenting here just an overview of the different safety measures that we have considered in European projects, for instance. How we are targeting the problems and how to solve such problems by inserting different layers in the core, absorbers, or sodium plenum, etc., so that we can do more safe designs. In comparison with other reactors, we will see afterwards other coolants, etc. There are comparative advantages in sodium cooled fast reactor. Fast spectrum, as I mentioned at the beginning, it produces less minor actinides. So compared to thermal spectrum, it has big advantages. For the temperatures, again, we are talking about high temperature coolant, so the thermal cycle is more efficient. Low pressure, it's also a good feature, and then the high extensive experience, not only for commercial, but also for R&D, small facilities. This will allow to make code validation or to improve the simulation of the system. And this can help in the future for designing more innovative. So as a conclusion, I just wanted to tell you that sodium fast reactor is ready for being one of the design for the small modular reactor. Even for this medium small size reactor, it has a larger safety performance compared to the biggest one. And then the integration of thermal energy storage is very attractive also for the integration of such systems in the future energy grid. Last point to mention is that for sure we need R&D, collaborative projects, and maybe IAEA is also here as one of the key actors in putting together many research and utilities together for pursuing this. Thank you very much for your attention.
Thank you very much, Sarah. Now I'd like to give a vote to another expert in liquid metal cooled technology, Dr. Mariana Tarantino from Italy, who will be explaining us what is the benefits of lead and heavy liquid metal coolants for SMRs. Please, Mariana.
Thank you, Vladimir. Good morning, everybody. Thank you for inviting me to present what we are doing on LFR. First of all, I would like to introduce why we are working on lead. This is something that will help the better understanding how our system are moving forward. So, as mentioned before than me from Sarah, with the lead we can provide to work on closing the fuel cycle. So this is increase the sustainability of our nuclear system, and also thanks to the use of lead, we can increase the safety because we have good performances in natural circulation and heat transfer, and we have a very good margin in terms of boiling temperature. So this will allow us to work our system up to atmospheric pressure, so we don't need to pressurize the systems. And also, thanks to the inherent property of lead, we don't need the intermediate loop as in the sodium, because the lead work very well with the air and the water. then led all of us to perform, let's say, operational systems thanks to the good retention of fission product and the high capability to shield gamma ray, and also the density could be advantages because this will avoid by, let's say, by design the problem of criticality in case of a severe accident. Of course, lead has also some drawbacks. First of all, the density. So this will something that we need to face in terms of seismic analysis, for example. So the pool configuration has been chosen for this kind of system. The melting point could be something that we have to face. So for this, we are designing provisional engineering systems for engineering features for reducing taking account the high melting temperature. A problem could be the opacity, because we need to provide in-service inspection in our system. And of course, as you well know, compatibility of structural material is a problem that we are facing in the development of the technology. So the use of this kind of coolant required the development of new technologies, new systems and components. So far, several work has been performed worldwide. First of all, I need to mention the strong activity that we are performing in the frame of the GIF activity. In the GIF, we are able to stay in touch with, let's say, all the players worldwide. So there, Europe is working with Russia, with the US, with Japan, and others, and China, of course. And it's worth to mention that in Russia, for example, Brest reactor is under construction. So the technological readiness level of this technology is large enough for taking it to, for considering the applicability to the market. And as you can see from this slide, many activities are ongoing in Europe in terms of R&D. Many activities have been performed in Italy, in Romania, in Sweden, in Belgium, and in Germany and other countries. So the technological readiness level of this technology is increasing day by day, and the maturity is growing up very quickly. So according to that, there are now industries involved in the, let's say, in the development of this technology for looking forward to support the decarbonization of the energy mix and to support the energy transition by 2050. It's worth to mention the activity that we performed for several years in Europe, involving also Italy for the Alfred reactor, supported by the Falcon Consortium. This is a consortium in which Enea, Rateni Siena, and Ansaldo Nucleare have worked for a while developing the technology, and presently we are working with our colleague from SEK to further focalize the efforts. Recently, Belgium is moving on the design of SMR LFR. This will take the opportunity, will allow us to have the opportunity to focalize the efforts. And so presently we are discussing, let's say, country agreement between, at the level of the country, an agreement between Italy, Romania, and Belgium, starting from the bottom. So first of all, we are putting on the same table the player, looking forward to have a common roadmap for the development of SMR LFR. Another important project to demonstrate the maturity of this technology are the activity performed by the Swedish colleague. There is the project supported by Akalla with the Sealer 55. It's worth to mention that this program is even supported not only by the country but also by the private investors. And the direction that they are looking for is still to have a compact primary system cooled by pure lead, but with a difference in the let's say in the solution for the material. They are developing innovative corrosion-tolerant steel, as well as they are developing uranium nitride fuel, very similar to what the people from Russia are doing for Brest, and compared to what people from Alfred reactor or other players are doing for the MOX with the MOX fuel. And the last but not least, it's worth to mention the big effort that is going to perform by Nucleo. This, let's say, we call it still a startup, but it's no more a startup. You see, there are involved 850 people on the project. They are investing more than €500 million in the project, with a huge R&D program, even developed this in Italy, in Brasimone, with the design team in Turin, but with the headquarters in France. They are planning not only to build up the reactor, but to build up also the MOX factory, looking forward to close the fuel cycle. And as you can see from this slide, they have in mind a strong R&D roadmap with a lot of facility being constructed in this year, and a very aggressive roadmap in which they are looking for to put let's say, the first kilowatt on the grid by 2033. So this is very challenging, but they are making very tough efforts on this, and this demonstrates how the LFR is ready for the market. So thank you for your attention.
Thank you very much, Mariano. Grazie Emilia. Now we move from the heavy liquid metals to the light gas reactors, and we'll see benefits, which will be presented by Mr. Frederick Reisma, the head of the Nuclear Power Technology Development Section. Please.
Thank you, Vladimir. So I thought to title more than just hot air. So hopefully I will, in a few next slides, show you that this is not only a promise, but it's been realized today, and but also show the challenges that lies ahead as we want to go to very high temperature gas reactors and not only high temperature reactors. So what's the reason people are interested in high temperature reactors? I think the increased temperature has been highlighted by many of the speakers for the other technologies. So high temperature gas reactors with an outlet of 750 and above, of course, get the advantage of good increase in efficiency. If you use a steam generator, and in the future, if you go to a direct gas turbine, of course, it can be substantially better. This is for electricity generation. It's also have a well-established modular high-temperature gas reactor design philosophy. And if you follow this philosophy, you can realize many of the inherent safety characteristics of the technology. So, I think today all the designers of high-temperature gas reactors follow this philosophy, and therefore, of course, have to still do all the work and show that this is true, but more or less can claim that the decay removal can be achieved by all natural means, that you have self-limiting power excursions due to a large negative temperature coefficient, and more importantly, very large temperature margins for your fuel. Of course, you have helium that is not reactive and doesn't influence the reactivity. So you can show that you can design the reactor to have no large release, and that all the radioactivity is contained within your coated particle fuel. And therefore, and this has been already, a case has been put to a regulator that the EPZ can be on the site boundary. And that was accepted. Also, you can achieve high burn-up. So I would say typically the minimum is about 80 gigawatt days per ton. But some of the designs aimed, and many fuel tests has been performed up to 200 gigawatt days per ton. It also have a flexible fuel cycle. Many studies has been done with plutonium and thorium, and some of this fuels has been tested in some of the previous test reactors. So the main characteristics important is the coated particle fuel, the helium coolant, the graphite moderator, and the slow transients. And what I showed on the right is the graph show releases from fuel at different temperatures. And basically, the operating temperature of fuel is typically lower than 1,000. This has been done to 1,600. That show you don't have any additional release in accident conditions. And you'll see the main releases only occur above 800 degrees. So large margins to inefficient product release coming from the coated particle fuel. So I think my next message, HDR ready for deployment. So several test reactors over the years, experimental reactors, some prototype reactors. There's currently 2 test reactors, one in Japan and the HDR-10 in China, that has gone through many safety tests and safety demonstrations. So there's a long development history of high-temperature gas-cooled reactors. We have the 2 types, the pebble bed that is shown on the right, and the prismatic type or block type shown on the left. They share many of the same characteristics. So the TRISA fuel and the slow transients due to a massive amount of graphite. And in Shindo Bay in China, the HDR-PM 200, so 2 units connected to a single power turbine, has been in commercial operation since December 2023. So what is the challenges? So I think typically we required high enrichment for HDRs. I think the minimum is about 8%. Other designs go up to high assay LEU to achieve the very high burn-up as shown. So a closed fuel cycle is also not possible in the thermal spectrum, although there's quite good utilization of plutonium, and it is a quite effective plutonium burner as well. To close a cycle, of course, you need reprocessing, or that's not been demonstrated at large scale, that the fuel can be reprocessed, although there's some good patents and demonstrations done in the past. The reactors, by this design to have these features, have a very low power density, about 30 times lower than a typical light water reactor. So, of course, to achieve then a sizable reactor, you need very big components. So, as shown to the right, the components are really large. I think the cost of the coated particle fuel is also, because it's quite complex, should always be slightly higher than other fuel options. I think the most important characteristics of HDRs are the high temperatures and therefore the process heat applications of this technology. We know that electricity is only responsible for less than 40% of the CO2 emissions, so the other 60% needs to be addressed, and that's where high-temperature gas-cooled reactors can make a huge difference with other technologies that also achieve high temperatures. So 50% of user industrial processes require less than 10 megawatt capability, so that also show that SMRs and therefore HDRs, that's all currently SMRs, is a good solution. So the interest, many different designs throughout the world, many projects at different stages of development, some of them already 20 years achieving good manufacturing of fuel, for example. I think more recently we have some of the newcomers, for example, Jimmy, that was successful in getting phase 2 funding from the France 2030 project. We all heard about Hatch that signed up with X-Energy to have process heat applications for their facilities. And now the new announcements that we heard about in the introduction. The HDR-PM that performed on this full scale, they performed a loss of cooling accident simulation. So really proven that this inherent safety characteristics is not only true for the small test reactors or for the AVR that did this already in the 70s, but also now on the full prototype or demonstration, commercial demonstration, I should say. And also the Shindo HDR-PM in April was connected to a local district heating, so also demonstrating this activity. And in August was announced that a large project with 2 light water reactors and 6 units of HDRs in one plant will be developed for specifically only steam production for a petrochemical industry in China. So the advantages, I think, is clear. The challenges, this is last slide on gas-cooled fast reactors. That's not my specialty, but just briefly, this is one of the other systems in Generation 4, so that have the advantages of the high coolant, but a fast spectrum, so it can close the cycle. But the challenges are that you need active cooling. It requires, therefore, active cooling of the fuel. if you lose your load, for example. Of course, the fast neutrons challenges, and with the helium, of course, you get dose effects on your vessel and structures, and it still requires a lot of R&D. Thank you very much.
Thank you very much. Thank you, Frederick. And our next panelist is Professor Jan-Lien Klusterman. He's going to talk about modular reactors. Thank you, Jan-Lien.
Thank you very much. Thank you for the possibility to speak here about the MSR. For those of you who don't know how the molten salt reactor works, you have a primary circuit with a fluoride or chloride salt with uranium and thorium dissolved in it, or uranium and plutonium, or only plutonium. And the heat is extracted via a secondary circuit to the energy conversion system. Because of the high temperature, this can be a Brayton cycle instead of a Rankine. There is a few options only for the molten salt reactor accessible. That is, you can withdraw a little bit of the salt every day, every week, clean it and pass it back to the reactor core. And you can also dump the molten salt in emergency dump tanks, or you can, because of the liquid form of the fuel, you can extract the decay heat with other means. But in any case, because it's liquid, it's easier than in other reactors, we believe. Here you see the reactor core of the molten salt reactor experiment that ran already for 4 years intermittently in the US from 65 to 69. There's not one molten salt reactor. There's a large variety of molten salt reactors. When you dive into the liquid fuel reactor science and technology, you get all different kind of possibilities that you can utilize, similar to the large variety of solid fuel reactors that we have. You can have molten salt cooled reactors, molten salt reactors with a thermal spectrum with graphite as moderator or other moderators. You can have fast reactors with fluoride salts, chloride salts, etc. So this gives you a large variety of options. And that's why I also tend to look at the generation 4 reactors in a different way, that you have at the one side solid fuel reactors with a large variety of options of fuels and coolants, and you have molten salt reactors, liquid fuel reactors, with also a similar variety of options. In the last 10 years in the European framework projects, we have worked on a molten salt fast reactor that you see here in the right bottom corner. And of course, of each of these reactors, you can have small modular designs as well. What are now the big themes in a molten salt reactor that we need to address? First of all, there is, of course, a material research area to understand the corrosion of materials in contact with salts and how you can avoid this corrosion. So it's at one hand looking at better structural materials, on the other hand also looking at mechanisms to clean the salt and to make the salt in such a shape that it's much less corrosive than you would expect. Secondly, in the core, you have a lot of reactor physics to be done. The liquid fuel, really, for reactor physicists, is a very nice research area because of the precursor that also circulate in your system. Safety analysis, of course, it's not only neutronics, but it's because of the liquid shape, always neutronics coupled to CFD, coupled to all kind of chemistry options that you can have in your code systems, coupled to mechanics. So it's really a multi-physics, multi-chemistry approach in the safety analysis. And of course we need huge data, a large database on all kind of salt properties that you utilize in your reactor. This is a function of temperature typically, this is a function of impurities in your salt, etc. So it is important that you also get a theoretical model to calculate all these properties. And so research is also being done in that field. Safety analysis of decay heat removal in your system is important, whether it is dump tanks or other mechanisms to remove decay heat from your system. Liquid fuel typically makes it easier, but it's not obvious, of course. So also this is something that needs thorough analysis. The extraction processes, so to clean the salt, so how to get rid of the gaseous fission products, how to get rid of the noble metals, other lanthanides, for example, in your salt. This all is a chemical processing plant that either you can attach to the molten salt reactor that you have online, fueling, refueling, or that you can do in a batch-wise fashion. Handling of waste, if you extract radioactive nuclides, you produce waste on the site, of course, that you have to immobilize, otherwise it will not help a lot. And then you need to clean up the salt, to make up the salt such that the condition is such that the corrosiveness of the salt is much less than if it would be impure. So these are the research areas currently in the molten salt research field. It looks like a large variety, but we are very lucky that we can apply small modular reactors, because in many cases we can relax a lot on these research themes if we go the way of small modular reactors. If a reactor is small, the decay heat removal becomes easier. If it's modular, you can replace components that were in contact with salt after, say, somewhere between 5 or 10 years. And if it's batch-wise fueled, you do not need all the online processing of salts, etc., but you can do it afterwards, after 5 or 10 years of operation. So the SMR concept is really on the critical path towards the implementation of large molten salt reactors. So for me, this is really something that we need to do, otherwise we will never get these large reactors. In these large reactors where you have online processing, there's so much innovation, so much new stuff that it will be very difficult to start directly with these large reactors. So we need small modular reactors. There is a lot of companies working on molten salt reactor startup companies, more established companies. These are not all working in the SMR field. Some of them are also working in the large reactor field. This is only in Europe and the US. There's also a couple of them, of course, in Asia, etc. So there's also a large variety in startups. And this reflects also the variety that you can have in the technology of molten salt reactors. If you look at the maturity level, there is some need for speed up. So the SMR development could help us in this. Currently, if you look at the NEA dashboard, its status of the SMRs in the field of MSR is around 1.5, with a strong focus on engagement and a little bit lacking in the other fields. So there's still a lot of work to do, but by combining forces both at universities, research laboratories and startups, I think we can make big progress in the SMR field. So for me, the long-term vision of MSR is, of course, to have a large reactor with online processing where you can have breeding of fuel on the site, either from uranium or from thorium, and have a clean fuel cycle where you can where all the actinides can remain in the liquid salt, and you extract only the fission products, and that's then eventually treated as waste. But we have to go through the way of SMR to make all this happen. Otherwise, to build a large reactor without the SMR development is a step too large, I think. There's still a lot of work to do, and below the questions of licensing, siting, fuel supply chain, etc., there's also a lot of fundamental research to be done. So in the Summer Far and Summer Safer projects of Euratom that was coordinated by TU Delft, we have now the Endurance project coordinated by Politecnico di Milano, and there they focus much more on the fundamental science needed by the startups in the molten salt reactor field. And I think this is really a very wise approach, because this is really on the critical path towards implementation of MSR. Thank you very much.
Thank you very much, Jan-Lin. Now I'd like to ask Ms. Sarah Eaton to review briefly these 5 technologies from the point of view of safety and regulation. Please.
Thanks very much. Let's just jump right into it. So the Canadian Nuclear Safety Commission is Canada's nuclear safety regulator, and my goal for this plenary session is that when you leave, you accept my view that risk-informed regulation supports innovation. So everyone will say to us in Canada, the world is watching, and I can assure you that we feel the eyes on us as we do our work. And we're approaching our licensing and our approach to regulation for small modular reactors using a three-pronged approach. The first is using our robust performance-based licensing process to review these technologies. We're leveraging our vendor design review, which allows us to have early engagement with industry to understand the novel features and for us to be able to explain Canadian requirements. And the third is our 5-year, $50 million project on small modular reactor readiness to ensure that our staff have the capacity and capability to review these designs to ensure that we can provide the clarity of regulatory expectations that industry requires. So, risk-informed regulation supports innovation. At the CNSC, we've engaged closely and connected with with industry to be able to understand the new designs that are being proposed in Canada, the novel features, and the innovative deployment models, which I think is a part of innovation that's important that we discuss. We also are looking at how we can better communicate our regulatory expectations with regards to innovative designs and these deployment models. And innovation can simplify reactor designs, but this needs to be backed by evidence. And so, do we need all this evidence on day one? No. That's the benefit of a life cycle approach. A life cycle approach allows you to look at information in an iterative fashion to be able to make more concrete decisions as you move through the licensing process. But we need applicants to show up with the level of detail that's necessary for that licensing stage. And we need operators to be a risk-informed customer, to be an informed customer, that they've done their own due diligence on these innovative designs, that they are satisfied before coming to the regulator to look for approval. We think that collaboration supports innovation. The US, UK, Canada trilateral memorandum of cooperation, we feel, is the global model for regulatory collaboration on SMR reviews. And the benefits are many. Training between regulator to regulator, staff exchanges, the ability to take a previously conducted review, leverage that and use that in your own technical review is a way to be more efficient, but it also adds robustness to your regulatory review process. And focused technology-specific collaboration gives us the means to be more effective and efficient. And as we have an opportunity to do more of this, I think you'll see the benefits of that as we move forward. And I think our collaboration has shown that when we work together, we're stronger. And I think that helps support nuclear safety. What we haven't heard enough at this conference is the importance, I would say the need, for robust engagement with the public and Indigenous nations and communities. And so if we don't have engagement with the public and Indigenous nations, projects will not be successful. This is a shared responsibility between vendors, operators, supply chain, and also the regulators. But we need to ensure that the public has access to technical information so they can understand these innovative designs, that information is shared in a way that's understandable to all levels. So to my mother who has no understanding of our industry, to those retired folks who have a lot of understanding in our industry, to be able to build that as we work through. So in conclusion, my takeaway today is that regulators are ready. Regulators are interested in innovation. They're interested in ensuring nuclear safety on these new designs. Using a performance-based, risk-informed approach allows us as regulators to work together, to collaborate, to engage with industry in a way that ensures that we're ensuring nuclear safety as we proceed through new novel designs. And I think timely regulatory reviews are absolutely possible, but applicants, operators need to provide the appropriate level of detail at the appropriate life cycle stage to ensure that those decisions can be made. And finally, I hope that you've heard my message on the importance of public and Indigenous engagement, that you have to approach this in the same way that you approach the reactor safety case. You need to have precision, enthusiasm, passion. You need to engage the right experts to be able to build a long-lasting program that covers the life cycle of your facility. And that's it. Thanks.
Thank you very much, Sarah. Actually, I have a question for you because you've touched on risk-informed performance-based, but I really want you to go a little bit deeper. How do you balance the need for innovation and regulatory efficiency with robust regulatory requirements?
So from our perspective, we know that there will be innovation within the industry. I would say for existing facilities, we see interest in being able to add the ability to produce medical isotopes in Canada. And so innovation is, I would say, not new for regulators and not new for the CNSC, but we see the pace certainly increasing. And so how we've approached innovation is to not be siloed. So to work closely with our counterparts, our international counterparts, but also to engage closely with the industry to ensure that we understand what the purpose of the innovation is, the approaches that they're taking, to ensure that we have the information we need and that our expectations are clear. And I think that's an area where it's important that we have an honest discussion on what the expectations are, on where the requirement comes from, the level of detail that's required specific to that specific life cycle stage.
Thank you, Sarah.
Perfect. Now I'd like to ask also a question to our representative from GIF, Mr. Stefan Sarat, about what are advantages of the advanced modular reactor, which you call here in the IEA innovative SMRs. What's the advantages if you apply these 5 of 6 GIF technologies to the small modular reactor? What's the main advantages? And what is of them is most promising for future development?
Thank you very much, Vladimir, for this very last interesting question. Of course, as a future GIF member and GIF chair, I will not give a prognosis for what should be the best concept. I think that you have to take into account that more than reactors, and in the case of GIF, more of the 4th generation reactors, you have to take into account several things. The first one is the technical readiness level. Is different from different concept. For instance, for sodium fast reactor, you have more than 400 years of cumulated reactor functioning in the world, compared to other one where you only have few months or few years. So, but TRL is not enough because you have to take into account that you have possibilities and potentialities. For instance, for molten salt reactors with a quite low TRL, you are on the other side a large amount of possibilities, of potentialities in terms of fuel consumption, in terms of non-proliferation resistance, because on SMR you can design in order to produce lower weapon-grade plutonium. You can even reach transmutation. Therefore, you have to take into account several things. And more than that, and we see that we saw that with the last news about Amazon, Google, and Microsoft. It means that if you have a great need, a need in energy, a need in electricity, I mean for AI, for data centers, and so on. Therefore, you need fast deployment of such system, and you can see that they invest in 4th generation reactor. So the main advantages that, in my opinion, and we saw that in the last meeting from GIF, is that with 4th generation, you can also achieve non-electric applications. I mean, you can produce, and we saw that with the HTR presentation, you can achieve production of heat for industrial application or for district heating. You can also, with nuclear 2X, reach the production of low carbon hydrogen. You can also apply desalination, and in the next future, you can also think about possible sustainable aviation fuel or navy fuel using those kind of reactors, because in 4th generation, they can provide higher electricity and high level of heat.
Thank you very much. Stefan, 1 minute, Frederick. Tell us what challenges exist in developing fuel elements and materials for the high-temperature gas reactors, in particular the graphite core or the materials subject to these high temperatures.
Thank you. I think the fuel technology has been well established, and the fuel plant in China is currently making 300,000 pebbles per year. And in the US, in the AGR program that's wrapping up now after many years, I think the manufacturing of the tricer fuel is well established and well tested to temperatures above 1800 degrees and to very high burn up. Graphite, we need new graphite grades. The grades that was tested in old reactors is no longer available. And of course, you need some irradiation experiments to understand the specific graphite properties. So there is some work, some new interest from graphite manufacturers to do irradiation tests on the graphite. So we'll say lastly, on the metallic side, currently for the high temperature reactors, the materials are available, but in future, if we want to really achieve the very high temperatures, I will say above 850 degrees outlet helium temperatures, we will have to qualify new metallic materials. Thank you.
Thank you very much.
Thank you very much, Frederick. Now I have a question to Mariana Tarantino, as expert in LFRs. My understanding is that lead-cooled technology faces significant material challenge due to corrosive nature of lead. With materials, what is the recent advancement in this area, and what is the current status of research and development on this material science?
Yeah, I know that material stuff is something that is scaring people when talking about LFR, so this is a really good question. When we started to work on LFR, I started in 2003. One of the main concerns was materials. People were aware that the lead is quite corrosive, but in the last 20 years we have made several progress, especially in the frame of European project, in the frame of international collaboration, and most recently also, let's say, with the involvement of industries. For example, it's worth to mention that in the frame of all of this project, we have well understood the mechanism of the corrosion. We have well understood that the corrosion is driven also by the coolant chemistry control. So this is something that we need to address very well and to keep coupled. And most recently, in the frame of the project, for example, in the frame of Falcon Consortium, we have developed let's say, very promising solution with the alumina coating with the stainless steel. Or other colleagues from Sweden are working on, let's say, tolerant steel working in lead based on a solution. Colleagues from Belgium have developed a lot of work on first on Mira, and now are working increasing the temperature on the solution. People from Nucleo are working on other solutions, like, for example, the use of alumina coating by different technique. So there are many solutions in place that are going to be now tested for the final, let's say, the final assessment.
Thank you very much, Mariano. And Sarah, you went very quickly. You wanted to touch on the current research priorities, but you went very quickly to meet your 7 minutes. So if you can just highlight for us, what are the current research and development priorities for sodium-cooled fast reactors?
Yeah, in that field, I have to mention that now the trend is changing. So in sodium fast reactors, we start with small reactors, then we end up with big reactors. Now we are doing the path forward. So now in research and development, we have to start looking on small modular reactors back. So it means medium-sized reactor, and then the safety is different. So our target now is to start looking at this size, because the neutronics are different and the core behavior is different. And then that's the point, including also passive systems, so that we can also demonstrate completely that we shut down the reactor, because the insertion of control rods are for sure achieved, etc. So that's more or less the topic now. Also including metal fuel. So far it was oxide fuel for MOX, oxide fuel for fast reactors, but now maybe metal fuel is also an option. So that's good.
Thank you.
Thank you, Sarah. Question to the Professor Klosterman. You noticed that the molten salt has many benefits. Could you just briefly, very briefly, highlight the main of the benefits and what specific applications of molten salt reactor would be really best, and from your point of view?
Thank you very much for this question. Yeah, I think the main benefits in the field of safety, for example, is that it's a low pressure system. Because of the fuel being dissolved in the fluoride salt, due to expansion of the salt, the reactivity coefficient is very large and negative. And the boiling point is really very high of these salts. But what I like most, for example, of the molten salt fast reactor is that you have a reactor at its most critical state, and whatever happens to the reactor core, it will always lead to a lower reactivity. So you need an active system to bring the reactor operational, instead of that you need active systems to shut down the reactor. And that principle is very attractive, I think. The benefits of the molten salt reactor are obviously as a part of a flexible fuel cycle system, where you can make use of the fact that you have already a fluid fuel that you can process more easily than if you would have a solid fuel maybe, and that you also can make the fuel more easily than with other systems. So it is really connected to a very flexible fuel cycle. That's the part where the niche where the molten salt reactor can excel, I think.
Thank you, Jan-Lin. So we have time for a couple of questions from the floor, if there are any. I cannot see. Okay.
Yes, please go ahead.
Okay.
Please go ahead, quickly.
Okay. Hello, my name is Nikolaus Müllner from Institute of Safety and Risk Research, Boko University. I have a question to CSNC on this risk-informed, performance-based licensing approach. As I understand, there is no other way than to go for risk-informed, since the prescriptive rule of regulation is very much targeted toward light water reactors. So for non-light water designs, there is no other way. My question is, do you expect this approach to be much faster than the prescriptive approach? Because you still have to do the safety analysis. It's just that the burden is shifted more to the designer and the vendor.
We understand, thank you.
Yeah.
They're going to be quick here. Thanks very much for the question. I think that the pace of which you can proceed forward with a regulatory process is truly dependent on what the applicant comes forward with. And so if you have the necessary information to show that you're meeting safety objectives, that you've done the work in the pre-licensing stage so the regulator understands your design, understands your approach, I think that you can have relatively timely decisions. I think first of a kind is slow and expensive, and I think that has to be accepted. But I think as you move through those iterative designs and you move to second of a kind, you'll have a lot of regulatory efficiency. But for the first of a kind, you'll need to be able to have the demonstrated proof that you can operate that you can build and construct that facility safely.
Okay, thank you.
Questions here?
Any other questions from that side?
Thank you, González, from the regulatory body of Argentina. My question really applied to many other reactors that we were submitted during this interesting conference. And thank you very much for the interesting discussion that we have on this type of reactors. My question is the following. It will be very difficult to imagine that one of these reactors will be acceptable if there is not a clear conviction that the first principle of the Vienna Declaration is being complied with. And the first principle of the Vienna Declaration is very demanding in mitigation efforts. And I have not seen a discussion on this issue, not only in the presentation in this session, let me say, but also in other sessions was the same. And I am concerned that nobody is referring to the Vienna Declaration and to the first principle of the Vienna Declaration for a number of reasons. This was adopted in an international conference by all the member states which are involved in this, etc., etc. And that is my question. I mean, what is your reflection about compliance with the first principle of the Vienna Declaration?
Thank you. Anyone want to answer?
So just to make sure we're all on the same page, so the first principle of the Vienna Declaration is about eliminating the sequences with large or early releases. So
who wants to
answer?
Stefan?
Oh, sorry, we mean elimination of what?
Yeah, sequences, accidental sequences with large
Sure.
and or early releases.
I think I'm trying to begin to start the answer. Of course, in the concept and the new concept, you've got here new concept for new markets and for new use case. So, of course, in terms of conception and only connected to public acceptance of the deployment of those future SMR or AMR, the concept must take into account all these facts. And when you are dealing with sodium fast reactor and passive system, it's a major milestone that you can achieve with such kind of reactor. Of course, you can go further with the start with the first generation reactor presented there. You are a limited request and demand of uranium resources, because main fast reactor are able to close the fuel cycle. So we are perhaps indirectly, but we are for sure taking into account all these facts and all the possible consequences of what should happen.
Yes,
yeah,
Sarah,
I can add as well this and support the point that, for instance, in sodium fast reactor there are medium size worldwide. It is like Monju in Japan, or in Germany it was the SNR 300 already licensed and everything. So in this size it was already considered all these aspects. So it's the so-called beyond design basis accident, where you consider what happened if we have this type of things, and the source term evaluation and the release of radioisotopes, everything is already considered for sodium fast reactors. Yes.
Okay. Thank you. Any question from the designers, developers, or researchers?
I think this will be the last one.
Yeah, please.
Good morning. I'm Benjamin Houdet from France. I work by Framatome, and I'm also a unionist. I have a question for molten salt reactors. Dealing with the salt is really tricky sometimes in operational conditions, and we have major phase change and major composition change regarding the raw materials that are used. So in your molten salt reactor research, do you face these phases change? Sometimes it's liquid, sometimes it's solid, and when it gets solid, it's very hard to be defreezed. Thank you.
Thank you very much. Yes, of course, this is an important topic in the research, of course. Freezing of the salt in the cold parts of your system. We are far away from boiling, so maybe that's not the issue, but you can have freezing, so you need a margin between your operational temperature and the lowest temperature in your system. But it's also important that in certain circumstances you can have precipitation of radionuclides. So that's also something that you have to investigate. That's also a function of temperature, etc. So all these things, you are fully right, I think, are part of the research program and should be part of the research program.
Okay, thank you everybody. Now time to finish this panel discussion and this session. And I'd like to thank everybody who joined us today, this morning. You showed very great interest in the small modular reactors, and in particular to the innovative SMRs. Of course, I'd like to thank our participants, and from what I learned here, that like Stefan explained it, these 5 technologies of 6 GIF technologies which are applicable to SMRs, considered SMRs. We have representative from all 5, actually. Frederick covered 2 of them. And what I learned personally is that for the moment, that we cannot say which would be the best or something. That for this reason, we understand that we should develop all of them. And for this stage now, today, there is no competition between these 5. This is actually require cooperation, especially international cooperation, to achieve our goals here. I want to also thank Anna, my counterpart, moderator. I believe it's another great example of cooperation between our departments, Department of Nuclear Energy and Department of Nuclear Safety and Security. And thank you for this, Anna. Excellent collaboration.
Thank you. This has been an exciting session to me and full of optimism and hope, also highlighting the work and energy that we are seeing and will continue seeing for sure in the coming years. So being a safety professional, I I want to highlight 2 things now. One is the significant effort that the regulatory bodies, and we've seen a clear example here, but we've also seen others during the week. So the significant efforts they are putting to be fully prepared to regulate innovative SMRs, setting up best practices for others to follow. And the second, for us, for the agency, it is essential that we continue or enhance our efforts fostering international cooperation, working collaboratively with GIF, with OECD, NEA, and all our member states to enable the safe, secure, and timely deployment of innovative SMRs. Thank you very much to our panelists. You were brilliant, and you gave us insightful and informative presentations and key messages to take with us. It's been a lot of fun working with you, Vladimir. Thank you very much to all of you for being here with us today, and please continue enjoying this amazing conference in this amazing city. Thank you very much.
something I had just about script through. Why do you think I let you get away with the things you said to me? Could it be I like you? It's so shameful of me. I like you. No one I ever knew or have spoken to resembles you. This is good or bad, all depending on my general mood. Why do you think I let you get away with all the things you said to me? Could it be I like you? It's so shameful of me. I like you. A magistrates bend the lies, hiding their mistakes. They look at you and and it makes them cry. And it makes them cry. Forces of command, they show their fat faces into mine. You and I just smile because we're thinking the same line. Why do you think I let you get away with all the things you say to me? Could it be I like you? It's so shameful of me. I like you. You're not right in the head and nor my eye. This is why. You're not right in the head and nor my mind. This is why. This is why I like you. I like you. I like you. This is why I like you. I like you. I like you. Because you're not right in the head, and nor am I. And this is why. You're not right in the head, and nor am I. And this is why. This is why I like you. I like you. I like you. This is why I like you. Say what you want. Don't play games with my affection. Take what you need, but don't leave me with no direction. It's dawn. No.
300.
On session 1-4, design.
But ain't committed no crime, so take what you can find. Forget what I say, 'cause I keep running away. I only live for today, but I'm one day behind.
From IAEA. In this session, we'll have 6 talks, 12 minutes each, and the Q&A session will follow once all the talks are completed. We'll have 18 minutes for Q&A session. So with that, I'm going to start the session. The first talk is on overview of modified design feature of Smart C. It's going to be given by Min Young Park from Kerry.
Good morning. This is Min Young Park from Korea Atomic Energy Research Institute. The presentation today will be on the overview of modified design features of Smart C. The contents of my presentation today are as follows. I would like to begin my presentation by introducing the SMR, Smart. Then I would like to briefly go over the overview of Smart. Finally, the design features of Smart C will be discussed. SMART, the System-Integrated Modular Advanced Reactor, is an innovative small modular reactor developed by Korea Atomic Energy Research Institute. It is an advanced integral type PWR with a thermal power of 365 megawatt. With its compact and integrated design, SMART provides an efficient and safe solution for power generation. Among its many advantages, SMART is capable of cogeneration. For instance, it can simultaneously generate electricity and fresh water, or electricity and district heating, making it ideal for countries seeking to address both energy and water challenges. SMART is capable of delivering 100 megawatt of electricity and 40,000 tons of fresh water simultaneously. Based on Korean consuming standard, this amount of electricity and water supply is sufficient for a city with a population of 100,000 residents. This slide shows the development timeline of SMART. Korea Atomic Energy Research Institute began developing SMART in 1997. During the early stages, conceptual design and basic design were conducted through successive projects. The Standard Design Approval Project was initiated in 2009. Finally, in 2012, the standard design of SMART was approved, marking the world's first SDA as an integral type SMR. Subsequently, Korea and Saudi Arabia initiated a 3-year project for the construction of SMART in Saudi Arabia. This began in 2015. This pre-project engineering project, PP project, modifications and advancements were conducted on the reactor power and safety features. And this resulted in the SMART 100 design. And finally, just last month, the standard design approval for SMART 100 was granted. We are now working on the development of SMART C, and this is the reactor I will be introducing today. SMART C is a variation of SMART 100 that emphasizes portability and economic viability. In order to describe the design features of SMART C, it is vital to lay out the design of SMART 100, as SMART C is a variation of SMART 100. The figure on the left shows the overall configuration of SMART 100 reactor vessel. The most distinctive feature is that it is an integral type reactor. Unlike conventional MPPs, major components such as pressurizers, steam generators, and reactor coolant pumps are installed inside the reactor vessel. Due to the internal installation of the major components, no large connecting pipes are required between major components. This eliminates the risk of large break loss of coolant accidents. The 4 reactor coolant pumps are canned motor pumps without pump seals. This inherently eliminates the small break loss of coolant accidents associated with the pump seal failure. The core is installed at the bottom of the reactor vessel. The reactor core consists of 57 fuel assemblies, and the fuel rod consists of low-enriched uranium oxide pellets. The reactor consists of 8 cassette-type once-through steam generators with helically coiled tubes. This design is chosen for its compactness and thermal efficiency. The upper section of the reactor vessel acts as a pressurizer. Electric heaters are installed inside the pressurizer in order to maintain the coolant at a saturated state. The figure illustrates the coolant flow path within the reactor vessel. The coolant, heated in the core, passes through the upper guide structure and moves into the annular region between upper guide structure and core support barrel, and then flows through the reactor coolant pumps before entering the steam generators. After passing through the flow mixing header assembly, the coolant re-enters the core. I will now briefly introduce the engineered safety features of SMART. The first passive safety system to introduce is the passive residual heat removal system. Single train of PRHRS is composed of one heat exchanger and the connecting pipes as shown in this figure. The heat exchanger is submerged in the emergency cool-down tank and it is connected to the main steam line and feed water line. The PRHRS is designed to cool the RCS to safe shutdown condition and to maintain that condition for another 36 hours. The second passive system is passive safety injection system. PSIS consists of two mechanically independent trains. Each train is composed of one core makeup tank and one safety injection tank with related valves and pipes. When actuated, the CMT outlet isolation valves open, resulting in the injection of the coolant in the CMT into the RCS through safety injection line by the gravitational force. The last passive system is containment pressure and radioactive suppression system. CPRSS consists of several tanks with related valves and pipes. When radioactive material are discharged from the RCS to secondary or secondary system, the CPRSS suppresses temperature and pressure rise in the containment and removes fission products. This slide highlights the difference between Smart 100 and Smart C. The main difference is in the size. The size has been optimized for transportability and economic viability. Reactor vessel size is optimized by modifying one of the main components, steam generator, while the containment building size is modified by optimizing IRWST and one of the safety systems, specifically the PSIS. These design improvements will be explained in the following slides. The volume of the reactor has been reduced by 45%, which was essential in achieving portability and cost effectiveness. This reduction is particularly important for utilizing Smart C in remote industrial fields such as oil mining in Canada, where access to electrical grid is limited or difficult. This was accomplished by replacing 8 cassette-type steam generators with a block-type steam generator. In the modified design, the helically coiled tubes are wrapped around the core support barrel, as shown in this figure. This new configuration maximizes space efficiency compared to the cassette-type steam generators, allowing for a more compact reactor vessel while maintaining the same thermal efficiency. Furthermore, the size of the containment building has been reduced by optimizing the design of PSIS. A new concept for the injection tank has been proposed. Instead of installing the core makeup tank and safety injection tank separately, a single two-stage tank has been designed. This design achieves 2 different injection rates by implementing independent injection lines with different orifices. This innovative approach simplifies the safety system, contributing to a smaller containment building size while maintaining the required safety performance. To summarize, an integral type SMR Smart 100 has been developed by Korea Atomic Energy Research Institute. It is one of the most promising SMRs with a high degree of development maturity, having gained standard design approval twice. A variation of Smart 100 called Smart C has been proposed. It is an advanced version with an enhanced portability and economic viability. Further detailed design will be carried out, and the feasibility of Smart C in various industrial fields will be evaluated. Thank you very much for your attention.
So thank you, Min-Young Park, for a great overview presentation of Smart C. Let's welcome our next speaker. The next talk is on heat distribution results from experiment using array of 5 sodium heat pipes, given by Pablo Diaz Gomez Maceo.
Good morning, everyone. In the next few slides, I'll describe 3 experiments we conducted in the high-temperature fuel channel lab of the Canadian Nuclear Laboratories using our 5-array heat pipe array experiment. Heat pipes are simple devices, simple in design, with almost no moving part except for the working fluid inside, and that are characterized by being self-regulated and are interesting as passive heat removal devices. They're currently being used in many different industries, especially for low temperature applications, less than 300 degrees Celsius. And there's an interest in alkali metal heat pipes such as sodium or potassium because they're adequate for higher temperatures to provide high heat transport abilities in nuclear reactor concepts. There's some examples here in this slide. The 3 that pertain the Canadian landscape are the Westinghouse Vinci, Dunedin Canadian Nuclear Battery, and the ACL Nuclear Battery. Highlighted is the Westinghouse Vinci since it's the one with further progress, and there's some interest of a demonstration reactor in Saskatchewan. I'm going to talk now about a little bit of methodology of the experiments we conducted, but first I'm going to talk about the facility where we executed those tests. It's a multi-purpose facility where that's designed for destructive testing, and we do different experiments from normal operation to accident scenario experiments. It's a test cell that enclosure that allows us to test high temperature and pressure experiments. And we have several devices to provide power and also high pressure gas systems up to 20 megapascals. The heat pipe array experiment is a 36-inch experiment that's composed of a heating block, 5 heat pipes, and a cooling block. The design of this experiment is meant to be vendor agnostic. This is due to the funding source. And it's going to be mainly meant for benchmark simulation codes and independent assessments. The characteristics of the heating block, it has the 5 heat pipes, 1 in the center and 4 around a 3-inch diameter. There's in total 12 channels where we insert cartridge heaters, 4 large heaters at 1.5 kilowatts in the center, and 8 smaller heaters at half a kilowatt on the outside. Mimicking the heating block, it's the cooling block, which has the same channels, but instead it's where the coolant flows. Power is applied to the heaters in a pulsing manner. For 100%, it's continuous power, but if we want to vary this power, we turn off the heaters in a total 4-second long period for a certain amount. For instance, the graph there shows a 60% setting and how it would look like. Measurements are done with voltage probes and current shunts for the input power, while the heat transfer characteristics are measured from the coolant, which are flow rate, pressure, and temperature. The experiment is instrumented with mainly thermocouples. We have 1 thermocouple per heat pipe, except for the central one in the heating block. And also we have 3 thermocouples that run vertically between heat pipe 2 and 5. Then we have 5 thermocouples, 1 for each heat pipe at the base of the adiabatic section, which is half an inch away from the heating block. Then at the midpoint as well, and 5 at the top, which is half an inch away from the cooling block. The cooling block mimics the heating block and also has 4 thermocouples, 1 for each external heat pipe, but not 1 for the central one. Additionally to that, there's 3 heat pipes that have a valve that allows a non-condensable gas, inert gas, to be injected into them and allows them to be disabled. Some of the preliminary test simulations were meant to allow us to design the experiments that we wanted to run. Now, moving on to results. The first experiment that we ran was a baseline experiment meant to commission the apparatus and show us the normal operation of this 5 heat pipe array. There were 2 thermocouples that failed, that then are showed as little x in that graph, and they will not be shown in the full results. In the first phase, we heat up the heating block using the cartridge heaters that I just explained, and as temperature increases in the heating block and reaches around 470 degrees Celsius, the evaporator and subsequently the adiabatic section of the heat pipe starts to heat up quite rapidly, which one would expect from a heat pipe. The coolant's already flowing, and it also starts to increase in temperature. After that, we allow the cooling block to reach temperature as well, which takes a little bit more time. And finally, when it reaches temperature, we did some tests to see what was the response of the heat pipes to different changes in power. Finally, we allowed the setup to reach steady state, where we measured the input and the losses in our system. Some interesting things to show here are the temperature difference between the base and the top of the heat pipe from 1 to 5, up and down. For instance, at 90 minutes, there's the difference between the top and the bottom of the heat pipe at around 43, 46 degrees Celsius. Then, once the cooling block reaches temperature, we see a decrease in this temperature difference down to around 10 to 20 degrees Celsius. And this difference is maintained all the way till the end, where we stop the test. The second test was a pulse power test and also a test to see what's the behavior of the heat pipes, the remaining heat pipes once we disable some of them. This test was thought about after we executed a similar test with a single heat pipe and we observed an instability. The point of the pulse power was an attempt to replicate that instability. Again, there's one thermocouple that failed. We pulse the heat pipe with a 5-minute period, and we can see an increase in temperature both in the heating block and also the adiabatic section of the heat pipe in the base, mid, and top, and a little bit as well on the cooling block. After minute 68, 2 heat pipes were disabled, and we observed that there's a drop in temperature on the mid and top thermocouples of the heat pipes that were disabled, as well as the cooling block, and an increase in temperature on the base and on the thermocouples near the failed heat pipes in the heating block. In this experiment, the cooling block did not reach temperature. Some interesting things to observe here are the temperature differences between bottom and top are similar to the ones observed at the beginning. And once the heat pipes are disabled, you can see that the minimum temperature difference, it's still quite high, and the maximum temperature difference is around 219 degrees Celsius, and it remains the same almost until the end of the test. The final test, we were doing a test to measure the transient non-uniform heating of the heating block. In this case, the heating was varied around the heating block while keeping the power constant. So to do that, we turned off a couple of the external heaters in sequence, creating a colder spot on the heating block. This was varied while maintaining the total input of the system the same. After 22 minutes, we put the power back to a steady state, or not a steady state, to a stable. And at 184 minutes, we disabled another heat pipe number 1. But this time we observed something different. Although the condenser temperature dropped, the bottom, the mid, and the top thermocouples in the adiabatic section of the heat pipe that failed did not spread out in temperature and actually became closer together, but all of them increased. You can see that on label HP1 around here, going up. Closer look to that, you can see that the failed heat pipes keep their high temperature difference, and it's worth noticing that heat pipe number 1, when it's failed around 183 minutes, the difference between the top and the bottom in the diabatic section is only 3 degrees Celsius and remains low all the way until the end of the test. So in summary, on the first experiment, measurements demonstrated the expected functionality of the sodium heat pipe array. For a second experiment, power pulses produce the associated heat pipe temperature fluctuations that we showed, and once to constant power, we did not observe that the fluctuations continued, such as the first instability we observed in previous experiments. Also, after disabling the 2 heat pipes, we observed the base temperature increase while the top decreased, which is what I would expected from failed heat pipes. For a third experiment, even though there was an oscillation, we did not observe that the oscillation was replicated on the cooling block while maintaining constant power, even though there was an oscillation on the heating block. And finally, after disabling the heat pipe number 1, it kept operating as if it was enabled. However, there was what suggests to be a reduction in the condenser length. Thank you very much.
Thank you, Pablo, for presenting results on your 5 sodium heat pipe experiment. Moving on to a third presentation, it's going to be on new CLO's R&D program in support of SMR LFR development and deployment. It's going to be given by Luciano Sinotti.
Good morning. You had already some insight on the Nucleo company by Mariano Tarantino this morning, and yesterday by my colleague Stéphane Calpena during the industry section. But I want to stress the fact that Nucleo is a fast-growing startup. I hired the first engineer the 1st September 21, and now we are more than 850 employees. We have offices in Italy, France, United Kingdom, Switzerland, and Slovakia. In the meantime, we have both 3 companies, and all the 3 companies are strongly engaged in our development program. Our mission is to design, construct, and operate a fleet of lead-cooled reactors of 200 megawatt electric and to provide fuel for our fleet of reactors. I want to remind that we have done the first pre-licensing process in France, and we have been selected by France 2030, and more recently by the European Nuclear Alliance. So our objective is to have in the year 2033 and ready for operation of our first 200 megawatt electric. But because in Europe there are no fast reactors, so operating with the fast flux, we have decided to build a 30 megawatt reactor, so a smaller reactor, to test new material and new fuel, so to be in condition in future to increase the operating temperature of the reactor and to increase the burn-up of the fuel. Obviously, we'll need fuel. Our reactor will be fed with MOX fuel, but on that we'll have more information this afternoon in advanced fuel section by my colleague Jean-Michel Marin. We are also obliged to do an important experimental activity that will be part of my presentation. So, our reactor. We are convinced that our reactor is feasible with all the information that we have, that is safe thanks to the technological choices that we have done and to the property of lead, which is inert towards air, towards water, and towards the MOX fuel. In terms of economics, what we have done, we have eliminated the intermediate loop thanks to the property of lead, introducing the steam generator inside the reactor vessel, and we had done an important effort to compact the reactor, especially in high of the vessel. So our 200 megawatt electric has a vessel of only 6.5 meter high. And this is a precondition to sustain the seismic load due to the high density of lead. The fact that we have a short reactor vessel allows us to increase the length of the fuel assembly with the dummy part till above the lead-free level to avoid a refueling machine operating lead. So our refueling machine will be only a next vessel refueling machine without any contact with lead, and the head of the fuel assembly are in full visibility. But obviously, this asked for a revolution of the layout of the primary system with several innovations and with innovative components. For this reason, we had to face an important R&D program, and because we have an innovative steam generator, the control rod are down upward operated. The shutdown rod are innovative. The decooler of the heat removal system are innovative. We needed to assess the emissivity of the vessel to have an alternative, a second solution to evacuate it to the outer surface of our reactor. So, we have planned at least 12 install facilities, most of them in lead, that had to provide us all the experimental data that are needed to confirm our design and to make the licensing process. Most of those facilities will be situated in the Brasimone site of ENEA. It is the site of our PEC reactor. When I was a young engineer, I contributed to the construction of the PEC reactor. It was a 120 megawatt thermal sodium cooler reactor, nearly completed, but has been dismantled. In any case, the building is still there, so after refurbishment can be used to install our experimental facility for lead. And so, we need at least 3 types of tests. Test of structural material, test of thermohydraulic components, test of mechanical equipment, and test of the whole behavior of the system to reproduce operational transient and some safety case of interest. So, in terms of mechanical test, obviously we have to face the corrosion in lead. So we have already available 108 positions for testing structural material in lead under control of the temperature and the oxygen activity. We have already Core 1, which provides us 32 locations for testing of specimen in flowing lead. And at the end of the year, we'll have also Core 2, will add additional 160 positions for specimen in flowing lead. In addition to that, obviously, it is necessary to have laboratories for mechanical tests, both in lead and outside lead. So we are doing an investment of above 150 million euro on that development. In terms of thermohydraulic, so we need to test fuel assembly, we need to test the steam generator, the primary pump, the heat removal system. And so we have a specific loop to face all those needs. In addition to that, we have a facility for fluid structure interaction, so to reproduce air-quake and sloshing. This facility will be ready at the end of the year. Fuel component handling is another issue. Handling in lead is more complicated than in case of light water reactor. So we had to simulate the possibility of extracting the fuel assembly from lead and to transfer it from the lead pool to the water pool. This asks for testing of this equipment and also on the associated rotating plug above the reactor roof. So in addition to that, we had to face an important program of in-service inspection, and at the end of the year we have a first equipment ready to simulate the in-service inspection on the outer vessel surface with lead inside. So finally, the precursor test facility. This is a facility of 10 megawatt thermal, electrically heated, which reproduce in scale the 30 megawatt electric reactor. So it will be full scale in high, but the cross-section will be proportional to the power to maintain the same power density, and so produce in as best as possible all the thermal transient and the case of stratification inside the reactor vessel. Well, I have to note that the feed water to the steam generator needs to be at a temperature at least 330, 335 degrees to avoid local freezing of lead. For this reason, we cannot apply the same procedure that we have been used, for instance, for Superphenix, to start up the steam generator. So we have elaborate alternative procedure that had to be tested. And for this reason, our precursor will be equipped with a turbo generator set. So in having the possibility to reproduce many of the transient, including startup and shutdown, in the best possible way. So this is the end of my presentation. And the only thing that I was just to add is the fact that all those facilities have to be finished before the year 26. So in 2 years from now, we have already four facility in operation. All the other facility had to be designed and constructed to start operating them and have the result in time for our licensing process. Thank you for your attention.
Thank you very much, Luciano, for great presentation of the nuclear R&D program and your reactor technology. Now I'd like to invite Dr. Dan Serbanescu from Romania Academy of Science to deliver a presentation on some safety and technology perspective for the new nuclear reactor types. Please.
Thank you. How can I proceed? Do I have to push something?
This one.
Oh, this one.
Yeah, this one top.
Okay. Thank you. I am Raw Power Technical Director. I have 45 years of experience in nuclear, of which 6 in PBMR project in South Africa, 20 in CANDU reactors, and other in VVR and PWR. However, here I will present the results of a set of evaluations we are performing in our country with in the context of evaluating the lessons learned from the way the nuclear program was going on so far. And we work with academics, with people from industry, with people from operation, and with a think tank of risk analysis at the national level called GLERUN. So behind everything I'm going to say, there are results and detailed things which could support the statements I'm going to make. So in order to evaluate, we are somewhere, and this question was 20 years ago in our case, how are we going to proceed further from the point of view of nuclear safety, not considering the political or economical factor for the beginning. So in order to have an approach which will give us credibility and give us confidence that we are not too wrong, we are proceeding in this evaluation looking from 3 groups of aspects. I call them facets. One is whether what we are going to do from now on is in accordance with the evolving safety principles. Not only safety, by safety we are actually meaning the fact that physical protection, safeguards, all those things, they became very tightly connected between them. And many times these things are discounted. The second type of approach is about the safety objectives. Article 1, Vienna Convention, what I would say, safety directive, Article 8C, yes, early releases, and many other things. But they are related to safety objectives. The third thing is nuclear power plant is not the technology of the core. It's an envelope of technologies. And I will show which are the consequences of this approach, which many times are not considered. So related to the first aspect, there are groups of criteria we have to consider. I will not stop at each of them. There are categories of issues, and they are actually illustrating the fact that we deal with a series of evaluations for which we have, in which we have uncertainties, big uncertainties. Another group of criteria is related to the fact that we performed safety evaluations for those plants. We want to evaluate the future plants, considering some safety criteria which are very well defined. In many papers and communications we had in the last 20 years, including in the agency related to safety margin and defense in death criteria and so on, we expressed our opinions and suggested some things, some solutions. In the meantime, in our case, we started to implement them. Another type of problem is that there are aspects which have indirect impact on the safety aspects, and I listed them here. So I will mention only one of them because in the last period of time, I realized that we almost discard this thing. Why are we building nuclear power plants? Why are we talking about concrete, metals, and so on? We are building for people. We are building not in one generation. We are building and operating for the next 2-3 generations. So the technology, human generation is maybe the weakest link in all these things. And the last are related to the fact that we are not building just one plant. Building a plant, that means that we are actually defining a new fuel cycle. Front-end, operation, and back-end. If we have, like in our case, other two cycles, this is a challenge. How to connect them, and which are the possible synergies, so that instead of simplifying the problems, not to complicate it. Here, that's the second approach, is related to safety goals. What I represented here, and I think 20 years ago, I presented in an IAEA conference. What you see in the lower part, which are some kind of S shape with a lot of bumps down, is the safety margin as we thought we have. The bumps are the real values of the safety margin we had, and this thing was shown to us by real life. Here I identified only the big accidents, but we see that a lot of smaller bumps almost all the time. So there is a difference between what we think that we achieved, what we think that we will achieve, and where we actually are. And we have to consider that. And when I hear declarations of physicists, engineers, that we build something that will not fail, I become very worried. Whatever human is building, it fails. If we don't have a plan B, what to do then we are lost. So there are various periods, and in each period, the paradigms how to deal with the safety objectives changed. In this moment, after Fukushima, we are in a new situation, enveloping and considering all the lessons learned so far. The first lessons were related to the criticality. Next were related to design-based accidents and transients like in TMI. Next they were related with the need to communicate if you have a bad accident. And the last one was related to the fact that you may have a catastrophic event. And you have to consider that. For instance, in our case, for the plants we are building, we are looking at the provision of the climate change for medium and long term. You may build a plant in a desert, and it will become a flooding area in 100 years, and vice versa. So this is so changing, this environment, maybe due to us, but we cannot assume that it will be forever like that. The last group of views on this potential approach, how to judge what is best, what kind of SMRs, for instance, to build. By the way, 7 years ago in IAEA, I had a paper presenting the lessons learned from what we had so up to that moment, and the fact that we may have a need for SMRs. 7 years ago. There were not too many. There were only 300 participants, and now there are 1,300 participants in such a meeting. So, yes, that evolved. What actually we have here is that technology changes. Each technology has its own timing, and we have to consider that because, for instance, now we see that we need for artificial intelligence more power. What if quantum computing will take over the existing now HPS? We don't know. So the type of plants for which we perform this evaluation are of three categories: water SMRs, gas SMRs, and molten salt SMRs. What you see here represented is one message I would like to pass, that we have to look not only at the quantity of energy, but also at the quality of energy. And that quality is called exergy. And in final analysis, the quality of energy to be transferred from the nucleus to the environment, we are very close to a generic approach to eco-evaluation of our plant. Now, these are various representations of the results of this evaluation. The conclusion is in the left side down. If we have to consider the real life, we are going to have research and development, a FOAC period, and a NOAC period. If we consider what is best in each of these periods, small modular reactors of water type seem to be better fit and available. The others still have to research. I'll give only 2 examples. Please have a look how many code cases in ASME we need for gas reactors, 17. Please have a look on the fact that we still didn't start to develop code cases for molten salt. So there is a way to go for this phase. For the FOAC phase, they might be comparable. That's what the picture shows. And for the NOAC phase, yes, they will be comparable. Per total, in my view, we need to get to the moment when a generation 4 will be fully usable and will take all the advantages they have, but considering that all the other phases were passed. I'll say only one thing and that I will finish. I am a physicist and engineer. As a physicist, I have the trend to continuously develop theories. As an engineer, I don't like that. I have a theory and I have to test it. If I don't test it, I don't trust it. I think that before we go on, let's test them. And then, when we are confident in that, to go on. Thank you.
Thank you very much. And now I'd like to invite John Jackson, Dr. John Johnson from the Idaho National Laboratory to talk about the microreactors and MARVEL program.
Thank you. It's a pleasure to be here with you today to talk briefly about the Department of Energy Office of Nuclear Energy's microreactor program, and specifically one of the largest projects we've got under that program called the MARVEL microreactor project, which is focused on design, development, construction, and operation of a very small microreactor. First of all, I'd like to take a moment to comment on microreactors in general. I don't know that we've touched on that explicitly in this conference. It's obviously a subset of small modular reactor, but from our perspective, microreactors are factory fabricated, transportable, and self-regulating. And adhering to these characteristics means that generally speaking, you have a thermal output of something less than about 50 megawatts and an electrical output of something less than approximately 20 megawatts. Clearly, from a strategic perspective, it makes sense to sustain our current light water fleet, the gigawatt scale reactors. In the United States of America, this represents over 50% of our clean energy production. So clearly there's a place. And then small modular reactors have been discussed at length in this conference, and clearly there's a role for them as well, and hence the urgent development that we see. So microreactors naturally fill out the lower power part of that options package, and enable us to have a broad spectrum of capabilities at our disposal when we're choosing our clean energy resilient selection for power production. So from a programmatic perspective, and this is one of Department of Energy's several congressional appropriated directed research and development programs, we focus on technology solutions utilizing the unique capability and expertise that exists in the United States of America's DOE laboratory complex. There are 17 laboratories. We utilize the unique infrastructure and expertise to address to find technology solutions to improve the economics or licensability of microreactors, because the essence of their limitations with respect to deployment at this point are economic and licensing. So naturally we focus on this. We're comprised of 4 technical focus areas. System integration and analysis looks at techno-economic analyses and regulatory support topics. Technology maturation is a place that we look at things like microreactor automatic control systems, characterization of robust structural health structural moderator materials like yttrium hydride, for instance. We had our demonstration support capabilities covered by Piyush Sabharwal in yesterday's session quite well. And then we get to microreactor application, which is integrated nuclear testing, and this is where the MARVEL microreactor sits. So MARVEL is an acronym. I've thus far avoided being contacted by the MARVEL lawyers, and we'll keep it that way. But it stands for Microreactor Applications Research, Validation, and Evaluation. The overarching goal of the MARVEL project is to move from a paper reactor, a so-called paper reactor, to a real reactor. There are hundreds or perhaps thousands of reactor concepts available on paper, but the trick is taking a paper concept and making it a reality, and that's what we seek to do. Again, the overarching goal of this project is to design, develop, fabricate, and construct, operate, and decommission a very small microreactor. It affords us the opportunity to train our engineering staff in preparation for demonstration of commercial concepts. The talk that'll follow will talk about some of the infrastructure supporting commercial demonstrations. But we need to prepare our workforce within the National Laboratory Complex, and this is one of the ways we're doing it. MARVEL will produce combined heat and power to a functional microgrid once it becomes operational. Very importantly, this is about sharing lessons learned with commercial developers. So all that experience we gain in the development and fabrication and construction of this microreactor and operation will be incredibly useful to the developers and to the NRC and other regulators, to end users. It addresses an age-old question, and that age-old question is, when can we see one in operation? There are no licensed microreactor concepts available at this point. So there's a lot of excitement surrounding it, and rightly so, but we need to make sure we do this the right way. So this is really about generating the momentum toward achieving that goal. On the left-hand side is a picture of the MARVEL microreactor at 90% final design. We achieved 90% final design, marking the first time we've done that with a DOE reactor in 2023, so last year. It is a liquid metal thermal spectrum reactor, natural circulation core coolant of sodium potassium. It is capable of generating about 100 kilowatts of thermal power, but we'll operate it at 85 kilowatts. We expect to connect a power conversion system. Pictured here is a Stirling engine concept. But it's very important to remember or realize that the Marvel reactor is designed to have removable and replaceable power conversion so that we can produce process heat, put a high-grade heat extraction system in to produce process heat for that utilization as well. So we anticipate being able to generate something on the order of 20 kilowatts of electric output. I will point out here, Marvel is not a commercial concept. That is not its objective. The objective of the Marvel reactor is to prepare our workforce and to do this and to have a collaborative platform for developers, end users, and industry to all collaborate on. Marvel has a 2-year design life. That is more of a policy issue. We're a research and development project, so we will at this point operate for 2 years. That's not a technical limitation of the reactor. Again, it's a choice we're making. It uses TRIGA fuel, Training Research Isotope General Atomics fuel. Weighs a little less than 8 metric tons and is about 15 feet tall. In designing Marvel and developing Marvel, we've relied heavily on several commercial codes as well as laboratory developed codes. RELAP 5 3D was used for the core thermal hydraulics modeling. As such, we need to validate these, so we have benchmark cases for all of these to ensure that we're getting accurate modeling and simulation. This is a top-down view of the Marvel core. It consists of 36 fuel elements. Again, uranium zirconium hydride, TRIGA fuel. It has a central void for a central insurance absorber for defense in depth. It utilizes a 4 control drum reactivity control system with boron carbide plates for neutron reflect or absorption. Coolant downcomer neutron detectors on the periphery. This gives a snapshot of the core system, starting with the fuel element on the left-hand side, core support structures, stationary core reflectors made of beryllium metal, and you see its location in the Marvel microreactor on the right. The fuel element is more or less a standard TRIGA element. The primary difference is that we use 5 5-inch fuel meats to comprise the fuel element rather than 3, so it's a little bit longer of an element. It is 30% uranium zirconium hydride, sourced from 19.75% high-assay low-enriched uranium. It has axial graphite reflectors on the ends, and then, of course, the beryllium metal reflectors around the periphery, as I showed earlier. If we look at the possibility of accidents, LOCA, for instance, we calculate that Marvel fuel will reach a maximum temperature of about 730 degrees Celsius, which is about 170 degrees Celsius below the expected threshold where you might have problems with TRIGA fuel. I talked about the reactivity control system. The central insurance absorber, when it's lifted out, enables criticality, which is controlled by the 4 control drums with the boron carbide plates. They each have individual control mechanisms. They are positively energized, meaning that in the event of an accident, if there's a scram, the energy is released, and as spring mechanism rotates the control drums and drops the central insurance absorber to ensure a less than 3-second scram target for seismic compliance. I talked about validation of the code. We have also built a primary coolant apparatus test for validation of the core thermal hydraulics. This is an electrically heated replica of the Marvel microreactor. You see it pictured here at Creative Engineers Incorporated in New Freedom, Pennsylvania. The primary coolant apparatus test was started up in September of 2023. We demonstrated natural circulation. I refer to this lovingly as my coffee pot, because that's essentially what we did with sodium-potassium coolant. The other thing we got out of this project, or this particular facility, is demonstration of the Stirling engines as power conversion in this environment. There are vibration issues associated with the Stirling engines that we need to address. So we've paused to reconsider our power conversion. We still can produce process heat. Power conversion will likely be relocated away from the reactor using a Rankine cycle or Brayton cycle, for instance. Very exciting. Because we've passed 90% final design, this is a real component. This is the guard vessel, one of 4 major structural subsystems for the Marvel reactor. This was completed in early October, so just a couple of weeks ago, and is very exciting because it's the first major component. We'll move on to the primary coolant system and reactivity control system this year, with construction expected to begin in 2026. We did learn a lot of lessons about welding that we solved, and this will be helpful for future commercial deployments as they work through some of the same issues. We will connect to a microgrid. The data is available. On the OSTI website that I've listed here, you'll find a Marvel utilization plan. Read it. This is an opportunity to get involved and get some value out of the Marvel microreactor yourself.
Thank you very much, John. Now we'll have the final presentation again from Idaho, delivered by Troy Burnett, again on microreactors. Please, Troy.
I don't know if it's harder to speak right after lunch when everybody's asleep or before when everybody's ready to go to lunch. But we'll try to see what we can do here. I'm not talking a lot about what technology is being developed, but what we are doing to help bridge that gap between research and the deployment of reactors. In 2019, the U.S. Congress passed a law through the Nuclear Energy Innovation Capability Act that established the National Reactor Innovation Center. And the National Reactor Innovation Center is located at the Idaho National Lab, the leading nuclear lab in the United States in Idaho. And one of our purposes is to partner with industry to bridge that gap from research and development to commercialization. And so what we are trying to do is to expedite that commercialization of nuclear power. And one way that we're doing that is to leverage the knowledge at the Idaho National Lab and across the Department of Energy sites to make it more readily accessible to industry. And so we have a lot of knowledge and expertise at the Idaho National Lab, but we also have a lot of connections across the United States and across the world with leading nuclear research. And so we are endeavoring to bridge that gap and make it more readily accessible to industry and bring industry partners in and work with them. One of the ways that we're doing that is by developing advanced test reactor test beds, where industry can come in, partner with us, and bring their reactors in and test in a controlled environment that's set up and that they don't have to go through that expense, and it's already got the safety and other support infrastructure, so they don't have to go through all the expense and safety and everything. It's already kind of built in to the program. And so we'll have those experimental facilities. We also want to try to leverage technology. There's been a lot of advances in digital engineering, digital twin, artificial intelligence. How can we leverage that to expedite the development process? And so we've developed virtual test beds. And we're also, as it's been discussed quite a bit here, one of the big problems that nuclear faces is costs. So we are also working on how can we reduce costs in nuclear construction, design, and everything. And so we've got a lot of things that are going on, but trying to, like I say, bridge that gap to help expedite the deployment of advanced reactors. And also we're doing a lot with maritime applications. There is a lot of interest in that perspective to nuclearize that fleet. So I mentioned what we're trying. One of the big things, the big efforts that we have is our test beds. We currently have 2 test beds that we're working at building and refurbishing. One is our dome. There's a brief comment on it yesterday. Actually, what we're doing is taking the experimental breeder reactor facility that's at the Idaho National Lab that ran from the 1960s to 1990s and refurbishing that facility to make it available for industry to come in and test their reactors inside of this facility. And so this, we believe, is going to be a great tool and asset for companies to come in so they don't have to build that infrastructure. And they can bring in their reactor and test it in a secure, safe environment. I think they mentioned, you don't trust it until you test it. Well, that's what we want to be able to do, is to provide that location where people can come in and test. And we have a nice, safe, secure facility where that can happen. We also have working on our Lotus facility, which I'll explain a little bit more here in a minute. But we're wanting to leverage the existing resources that are already there that the United States labs, the Department of Energy has, and make it more accessible to private industry. And there's a lot of capabilities there. Here's just a little bit of explains about what the capabilities of our Lotus test bed is. It's for, the primary purpose is for fuels that are enriched a little bit over 20%, that they can come in and test in there and have that safe environment. And we just completed our final design on this, and we'll be moving into getting construction contracts and getting that in place where we can get this built and ready for people to come. Our dome facility, it's going to be a hazard category 2 facility and provide safety class confinement, and has a pretty good floor space where people can come in and bring their reactors to test. We've had to do some modifications. When the ABR2 dome was originally built, it wasn't built to be able to bring large equipment into the facility and pull it back out. And so we've had to do a lot of refurbishment on the dome, and it's currently under construction and happening and taking place right now. And we expect to have it completed and ready to accept reactors in the 2026 timeframe. And that's going to be real exciting. But what it will do is it will provide that main background so that we can pull out the residual heat. We'll be able to dump heat from the reactor. We'll be able to supply the support air, water, whatever it might need, electricity to power your reactors. So if you're going to build a car and you're building a new engine, you want to be able to, you don't want to necessarily have to build the whole car, but you want to be able to test that engine. You can just bring your engine, that nuclear reactor, into our facility, and we'll be able to help test it there. Last year, there's one of the other big comments has been on partnering with government and private industry. Last year, the Department of Energy made $4.5 million available for industry to come and work with the National Reactor Innovation Center in our front-end engineering and experiment design process. In that process, we just recently completed with Westinghouse and Radiant, entered into our process, and they've completed their safety design strategy and a preliminary safety design report and a conceptual safety design report. I'm waiting for approval back on those, but that's really exciting that both Radiant and Westinghouse are moving through that process. This next year, the Department of Energy has made available $5 million to continue on into our next phase of the process, and we hope to be able to be moving forward with that here soon. And so it's progressing and moving forward. And so, to help industry get those reactors, get their designs from concepts to reality sooner. So what are those benefits? Like I mentioned, we're trying to be able to provide as much financial assistance as we can, but the technology is to be able to bridge that gap. The regulatory, these reactors will be authorized under the Department of Energy, but we think it's going to save industry a lot of time and resources to come and work with the National Reactor Innovation Center and the Idaho National Lab to be able to bring these small modular reactors, advanced reactors, to commercialization in a more timely manner. Anyway, thank you very much for your time.
Okay, thank you very much. Now I just want to invite all experts presenting today to this podium. And we have like 15, even more, 20 minutes, thanks to Troy to be brief for discussion. And to start with, maybe if Troy is here, I could ask a question. Why do you call this thing microreactor, which is when we have the nice measure in like kilowatts, watts, huh? You can make 1 gigawatt, 100 megawatt, 20 kilowatt or 20 megawatt, as you said, but you prefer microreactor, which is 1 million of the normal, right? That should be 1 kilowatt reactor. Who can take it? John?
So this gets into an interesting discussion about space reactors and terrestrial reactors, I think. And generally speaking, when we're talking about some of these remote deployments and some of the initial deployment locations for microreactors, we're talking about power sources in the vicinity of 1 to 5 megawatts to be effective and to make sense from an economic perspective. So I think, clearly there are technologies that are required for very averse environments like space, lunar projects, Mars. But for terrestrial applications, I think we need to be in that 1 to 5 to 10 megawatt range.
Okay, thank you.
So, Troy, I'm going to ask you a question. I think we heard a lot about SMR designs, challenges, and you talked about NREC objectives and goals. And again, you talked about using or utilizing existing infrastructure. So, of course, if we can, we should always use existing infrastructure. So my question to you is, if you have to highlight key lessons learned from NREC, even though you're using existing infrastructure, I'm sure there were a lot of lessons learned in that process. If you could share a couple of those with the group. It's on.
That's easy. So there's been a lot of lessons learned. One of the things that we've learned the most is this has never been done before, where a private reactor has been tested at a Department of Energy facility. And so, the Idaho National Lab has tested over 50 reactors on their site, so they know how to do that. But we've never done that with private industry coming onto the lab. And so where this process hasn't been set up before, we've had to learn along the way. And so it's been key to working with the industry all the way along to understand what their needs are. And also for them, they've never worked with the Department of Energy before. They've worked with the NRC, but not with the Department of Energy. And so there's a lot of similarities, but there's a lot of differences. And so that early engagement, and I think it goes for the NRC as well, just that early engagement, just sharing is a huge lesson learned, and that we can all learn from each other. And so we've given a little bit, private industry has given a little bit, and we're learning and developing a program together. And I think by working together, we're able to build a better program that meets the needs of both the DOE and private industry. And hopefully it will also reduce cost and also keep safety where it needs to be.
But is this bed only for water-cooled reactors, or like Westinghouse can send the LFR to test it?
So on the dome, it's the only thing that's limiting us is our 20 megawatt thermal is as high as larger reactors we can test, and HALEU fuel. Other than that, it's open. Bring your ideas, bring your dreams, and we'll figure out how to make it work. The ones we're looking at right now are high temperature gas reactors, and so they're both just enriched HALEU fuels less than 20%.
I see Luciano is very interested to bring his amphora-shaped reactor to test. Okay, now we have the questions from the audience. Please, Miss.
Okay, my name is Fitria from Indonesia. I have two questions. Is that okay? Or just
one, please. No, one, please. Okay.
Okay, so I will choose this. Okay. About microreactor, is it possible for us to design a microreactor just simply by scaling down the existing SMR, I mean. So we make it small from the existing nuclear reactor. And in your opinion, what is the most suitable SMR type to be a microreactor, to be scaling down? Okay, that's...
Actually, they're not from European Union, but first question.
So the dominant concept for microreactor development is the high temperature gas reactor concept. I think that has to do more with the technology readiness of high temperature gas reactors than anything else. I'm aware of molten salt concepts. I'm aware of a light water concept for microreactors. Fast reactor concepts, essentially a microreactor can be any, but again, high temperature gas seems to have the highest technology readiness levels, so that's why you see a proliferation of those in microreactor space.
Yeah, please, next.
Well, thank you very much, Kamal Mrabit, Morocco. Let me start by thanking all the presenters for their excellent contributions. I have a few questions to the colleague from South Korea. This is really minor questions on smart C, reactor. When this you expect this would be operational? Second, as this reactor has different, applications, including, district heating and seawater desalination. In respect for seawater desalination, what would be the capacity, the thermal, capacity for seawater, desalination? And third is certainly or consider artificial intelligence in operating this type of reactors. Would be happy to hear, or you could shed some light on this. And finally is really on the load following, exactly the compatibility with using this type of reactors with renewable energy, solar and wind. Thank you.
That was several questions. I will answer from the first question. What was the... that is actually our main priority that we want to achieve. We want to build this paper reactor as soon as possible. We're talking to many countries and many buyers, but at the moment there's not a specific plan to build this plant. Yes.
Mm-hmm.
And the second question was?
This was for the thermal, seawater desalination. What would be the capacity roughly? How many tons per day?
Tons.
Yes.
You can produce 40,000 tons per day per 10 megawatt electric.
Mm-hmm.
So that would be 11 times that amount.
Mm-hmm.
That would be the maximum amount of freshwater supply. And we are this smart is designed for load follow. It has a capacity to load follow with the renewable energies.
Okay. Mm-hmm. And artificial intelligence?
It would be great to use AI in control rooms or MMIS, but this has to be legally possible.
Mm-hmm.
It needs to be approved by the regulatory bodies. At the moment, SMART does not adopt any AI technologies.
Okay, thank you.
Very much.
So thank you for the question, but to be fair to the audience, please restrict your question to one, at the most have a subpart, but not few questions. So I'll make sure everybody gets an opportunity to ask. Just a quick one to follow up on the desalination. Do we know the process? Is it going to be reverse osmosis, or do we know what process are we looking at?
No, I asked thermal. This is only, yes.
Okay. No, but...
We have conducted feasibility studies on the desalination. We mainly looked at the RO process and the MED process.
Multi-stage, yeah. Thank you. Yes, sir.
Gonzalez from the Road Authority of Argentina. I would like to follow up with the question of my friend Hamar to Korea. As you know, the previous president of Korea declared that Korea would be a pro-nuclear country outside Korea and anti-nuclear country inside Korea. Would this mean that the Korean reactor will not be built in Korea, but you are waiting to build that reactor outside Korea?
The current president is very friendly towards nuclear. I think you're talking about the previous president, yeah? The current president has plans to build nuclear plants domestically.
For change of policy?
Yes.
Yes.
Thank you.
Yes.
And this is probably political questions that is difficult to answer because we have technical experts here. Any other questions from this side?
I'll ask a question to Dr. Sabenzo. There's a question. Yes. Please go ahead.
Nicolas Müllner from Institute of Safety and Risk Research. I have a question about licensing of microreactors. We heard on Monday that Finland was considering it a problem to have a lot of microreactors. Would they all need a site license? Are there some considerations on the licensing of hundreds of microreactors in the United States? How would this be handled?
So I can't speak for the regulator, but I've heard of concepts involving perhaps several centralized factory locations for processing and some addressing some regulatory aspects. When it comes to deployment, I think that's something that we're figuring out. Again, I can't speak for the regulator, but I know it's being considered, and there are multiple models being considered for licensing and regulating microreactors.
Okay, thank you. Any other question?
Yes, please.
Thank you all for your presentations. My name is Maud Baumann. I work for the French Ministry of Energy. My question comes as a reaction to the presentation by Nucleo, Mr. Sinotti. You said that Nucleo's mission is to develop your AMR, but also to operate it. I thought that this was interesting because there's a real question of whether all the new technologies of SMRs will be, sold to existing operators, or are new operators of SMRs going to emerge? I don't know if you can confirm or comment on that.
So, we want first design and construct, and later we will see, but we want to organize ourselves also as operator if we don't found a good agreement with other operators. So we are very ambitious in our mission. So you see that we start from the fuel cycle, and so we want to cover all the activity, excess reprocessing. No, we don't want to be directly involved in reprocessing because we consider that is a state mission because of non-proliferation and so on. Even if we have some attention to the process, so we want also to evaluate the different processing scheme, but for technical information not to be directly engaged. But we want to cover all the other aspects.
Okay, I'll go ahead.
Thank you. I have a question to Pablo. So how much heat you can ultimately remove? I mean, what could be this with this heat pipes technology? What could be the largest, biggest, highest power of the reactor in this case?
That would depend a lot on the design of the particular heat pipes being used. For instance, the one we use for our experiment are 2 kilowatt heat pipes. We have 5, so that's 10 kilowatts that we could remove from our particular experiment, but that doesn't mean that it's limited to that. It depends a lot on the design of each particular heat pipe.
But let's say 1 megawatt microreactor, or it's smaller. what is the ultimate size, with this technology? If you have, let's say, 1,000 heat pipes, probably it will not work, huh? And then you use pumps and coolants, but just for your estimation, what could be the highest reactor power using this heat pipes technology?
I think that the answer is the same. It depends on the design. You can also have...
So, any?
Hey, so I can just jump in. We're working with Westinghouse, and theirs is as he mentioned, is a heat pipe reactor. The one that's going to be coming in to our facility is a 3 megawatt, but their Vinci reactor that they're designing is 50. So I believe it can at least go up to 50, and I don't know about above that.
Okay, thank you for clarification.
So just a follow-up on heat pipes, since you're talking about that. So any particular modeling tool that was used to predict performance of heat pipe that you can talk about? And also, how do you remove heat from your condenser side of the heat pipe?
We remove heat from our condenser using air. Some of our experiments we've used helium as well. We want to keep the cooling block a little bit high in temperature so that it turns on the heat pipes faster. I'm sorry, what's the first question?
And a modeling tool that I looked at for the performance.
We do not do ourselves we do not use the modeling tools, but we do produce data for modelers. And if I remember correctly, the modelers use Ariant, a code that we have in the Canadian Nuclear Labs.
Okay. Thank you.
So any other questions, or we are ready for lunch?
There's a question in the back, yeah.
Was the last?
Thank you very much. My name is Louisa Mpede from South Africa, the regulatory body. My comment is on the Marvel microreactor. You indicated that you experienced a distortion on your welding. Do you want to just give us some update on how that was addressed, what led to that, and also whether it's addressed? Thank you so much.
Sure, and I appreciate the question. It gives me an opportunity to expound on something that we learned a lot of lessons in. When we also, by the way, learned quite a bit about construction of fabrication of these systems when we built the primary coolant apparatus test. And we had a subject matter expert, a welding subject matter expert with the Idaho National Laboratory who worked through these issues with the primary coolant apparatus test, so that by the time we got to the guard vessel fabrication with an industrial entity, we understood how to brace the system, for instance, to prevent weld distortion, how to post-weld anneal. Some of these things that appear to be simple and well understood in manufacturing space, we continue to run into problems when we build these systems for the first time. But it's very important to understand that as we work through these, we learned, we kept records, we were able to fabricate the guard vessel in a much faster time as a result of our experience with the primary coolant apparatus test. But it amounts to localized heat treating. It amounts to fabricating bracing structures to mitigate against this. We've learned a lot as we work through this.
Perfect. So keeping time in mind, before we conclude the session, let's thank our speakers one more time. And thank you all for coming and participating. That concludes the session. Thank you.
just like that. Oh no, it's not the things you do that tease and hurt me bad, but it's the way you do the things you do to me. I'm not the kind of girl who gives up just like that.